Reality at its deepest level is quantum mechanical, a world governed by rules that often defy our everyday intuition. We have come a long way from the times of Richard Feynman in terms of technology to the point where engineers and scientists have made significant strides in building actual quantum computers. But with the dawn of what is being called the quantum era and a constant flood of headlines about breakthroughs, it has become increasingly difficult to separate genuine progress from hype. And this matters a lot because quantum computing is not just a fascinating scientific endeavor but also an area attracting enormous investment. And when stories are told selectively or concepts are oversimplified, misconceptions and unrealistic expectations easily take hold. In this video, we will cut through the noise and take a closer look at the reality of quantum computing, separating what is possible today from speculation. From early times, light itself revealed the strange rules of the quantum world. In 1801, Thomas Young's double-slit experiment showed that when light passes through two narrow openings, it doesn't behave like tiny particles but spreads into a delicate interference pattern, proof of its wave-like nature. A few years later, Joseph Fraunhofer extended this idea with single-slit diffraction, mapping out the precise intensity of fringes and turning wave optics into a quantitative science. By the late 19th century, ever more refined experiments from airy rings in circular apertures to Fabry-Perot cavities revealed that interference was not a curiosity but a deep principle of nature. Interferometers like Max Zehnder then pushed the paradox even further, suggesting that a single photon could travel down two paths at once. Add a small delay in one arm and you can steer which detector lights up. Now at the dawn of the 20th century, the ultraviolet catastrophe showed that classical physics could not explain black body radiation, leading Planck to the radical idea of quantized energy. And just 2 decades later, the Stern-Gerlach experiment confirmed that even a particle's spin is strictly discrete, leaving no doubt that the quantum world defies classical intuition. And Schrödinger's equation provided the framework for what we know today as quantum mechanics. It helped explain weird quantum phenomena such as tunneling. Classically, if you don't have enough energy to clear a barrier, you never cross it. You hit the wall, bounce, lose a bit of energy to friction, and settle down. Quantum mechanics, however, plays by different rules. A particle is a spread out wave, and that wave can leak through a barrier even when the average energy is too low. And that leakage is what's known as quantum tunneling. In a similar fashion, it also provided an explanation for superposition, where systems exist in many states at once, something we all associate with the popular paradox of Schrödinger's cat. And these strange principles became the foundation for quantum information and ultimately for quantum computing. Now, to understand how quantum computers function, let's first turn to a classical computer. Classical computers follow a simple logic. Each calculation takes a definite input and produces a definite output. Quantum computers, on the other hand, work with superpositions of inputs, exploring many possibilities at once. At first glance, this seems like an enormous advantage. But when we measure the system, the quantum state collapses to a single outcome and much of that hidden richness disappears. What often gets hyped is the idea that quantum computers can do all calculations at once, as if they were infinitely faster than classical machines. But that picture is misleading. The real challenge, and hence the real opportunity, lies in finding ways to use interference to steer a quantum system towards the answers that we want. Now, when people talk about superposition, it can feel a bit abstract, but the block sphere helps us in understanding and visualizing the concept. Any pure qubit state can be seen as a single arrow on this sphere, and as the state evolves, the arrow sweeps around. That rapid motion you see captures how quantum states explore combinations of 0 and 1 continuously. To describe that motion precisely, we use two angles, theta and phi, and any state vector can be described by those two angles that map neatly onto three-dimensional space. By controlling these angles, we can move the state vector smoothly across all possible combinations of 0 and 1, the essential flexibility that distinguishes qubits from classical bits. So let's go ahead and try to understand in what other ways quantum computers are different from classical ones. First, gates. Classical gates map input bits to output bits by fixed rules. Quantum gates, on the other hand, are reversible rotations that reshape amplitudes and phase. This is what sets the stage for interference before a measurement picks one outcome. Now, there's one defining constraint when it comes to copying information. Classical information can be copied perfectly, but an unknown quantum state cannot. Let's think of it using an example. Let us consider that a qubit is like a firefly that may blink or not, that is, choose to stay dark, and copying it would mean we have to handle both combinations of blinking or not blinking at the same time. But when we try to do that, we would see that unwanted cross terms would appear, which means that these are impossible combinations of blinking and dark together. Those extra terms break the rules of probability, showing why a universal quantum copy cannot exist. A universal copy would have to reproduce every superposed possibility at once, and linearity forbids that, or else the probabilities would not add up. This is popularly known as the no-cloning theorem in quantum information, and it quietly shapes everything underpinning security ideas like quantum key distribution. And when it comes to computation, it means that we can't fan out a qubit the same way we duplicate a bit. That is, in classical computing, one signal can be broadcast to as many places as you like. This is called fan-out operation. But qubits do not allow this. Instead, circuits must steer information through unitary gates and shared correlations using entanglement. While this may look similar to broadcast, it's actually very different, and it's rather a special correlation between particles. Performing a measurement on one qubit instantly tells us something about the other. But this is vastly different from copy-pasting information. The simplest example of entanglement is the Bell pair. Two qubits, once linked, produce results that are correlated in ways no classical system can reproduce. Rotate how you measure them, and the correlations follow a precise quantum pattern, falling off like the cosine of the angle between settings. Even so, each side on its own looks completely random. There's no hidden broadcast and no faster-than-light messaging. What this circuit really shows is that entanglement is neither copying nor signaling, but a uniquely quantum resource that ties outcomes together in a way that classical world never could. So we just understood that entanglement shows us how quantum systems can share correlations that defy any classical picture. But to actually use those correlations, we need to read them out. And herein lies a deeper challenge. Unlike a classical bit, which can be checked without disturbing the state, measuring a qubit doesn't directly reveal its state. In fact, a measurement on the state changes it, collapsing the superposition into a single outcome. This fragility makes measurement both the power and the limitation of quantum information. Quantum teleportation is a striking demonstration of these rules. Let's say Alice and Bob share an entangled pair of qubits. Now, in the teleportation circuit, we first prepare a qubit in an unknown state psi, and the other two share the entangled pair. Alice's joint measurement consumes her local state, turning it into two classical bits that carry no information about the state psi itself. Across many runs, those bits are random. 0, 0, 0, 1, 1, 0, and 1, 1 all show up with more or less equal frequency, which is exactly what you should expect if nothing about those amplitudes was leaked. Their only role is instructional. One bit selects whether Bob must apply X, the other whether he must apply Z. And after those feed-forward corrections, Bob's qubit matches the original state psi every time, even though the state never physically traveled. The entanglement resource is consumed in the process, no copy remains with Alice, and nothing moves faster than light. Now, another point to discuss is information per use. In classical information theory, one signal can carry at most one bit per use of a channel. Quantum states seem richer since a qubit can point anywhere on the Bloch sphere, but the Holevo bound tells us that the extractable information per qubit is still limited. In other words, we don't get infinite bandwidth from quantum mechanics, rather the advantage lies elsewhere, in how quantum systems process information and not in how much raw data they can hold. So by now, you should have a fair idea that quantum isn't a turbo bit for everything. It's a different toolbox from classical computers. And complexity is the essential map that allows us to check which problems yield to deterministic steps, which benefit from randomness, and where quantum interference actually shifts the boundary. To briefly give you an idea if you're unfamiliar with complexity classes in computing, let's take a look at some examples of each class. So let's start with P. These are the problems we can solve efficiently in polynomial time with deterministic algorithms, and you can think of shortest paths, spanning trees, matchings, etc. Next, BPP. These are the problems that can be solved in polynomial time with a bounded error probability. So here, some tasks like primality tests and Monte Carlo estimates get easier in practice through the incorporation of randomness. Next, we have non-deterministic polynomial time, where checking a proposed solution may be easy, but actually finding one can cause the time complexity to explode combinatorially. And we have some famous puzzles here, from graph coloring to finding Hamiltonian cycles. Finally, we have the quantum region, PQP, which consists of algorithms that should run efficiently on a quantum computer by leveraging quantum phenomena like superposition and entanglement. This is where we classify quantum algorithms such as Shor's and Grover's. But here's a reality check once again. BQP is not a magic key to all NP-complete problems, and as you would have noticed in the Venn diagram before, it doesn't swallow up NP completely. So this further highlights that quantum structure pays off only in some specific cases, while still depending on careful data access and error control, rather than shifting all the boundaries. Now we are ready to look into some quantum algorithms, and let's start with Grover's algorithm for unstructured search. And to keep things fun, We are going on a treasure hunt. After all, who can resist the urge to look for strange grimoires and treasures? Frieren most definitely can't. Now let's look at what happens when we conduct the search classically. So we open the chests one by one, and on an average we check about half the row, so time in this case scales linearly. Now the quantum version starts with an even guess over all the chests, then repeats two moves, a black box mark on the winning chest and a global nudge that boosts its odds while dimming the rest. After a few iterations, the probability distribution tilts towards the correct chest, and after about the square root of n rounds, a single measurement picks it with high probability. The circuit logic mirrors this. Hadamard gates prepare the even spread, and the oracle does the marking, while the diffuser reflects around the average to amplify the target, and then we perform the measurement. As you can see, this would be something useful for Frieren. With a bit of quantum magic, she'd run into far fewer mimic traps. And that wouldn't be by breaking the rules, but by needing far fewer peaks before finding the real treasure. Now, coming out of Grover's algorithm, we switch from searching to looking for a hidden rhythm. For instance, consider a beacon that flashes light in different directions and at different intervals, and say we want to find its period. Now, this problem of finding the period is the crux behind finding prime factors of numbers and forms the basis of Shor's algorithm. And what comes in handy here is the Fourier transform that turns that repeating pattern into sharp preferences for certain readouts. Now the trick behind factoring is that the function you get when you raise a small number to growing powers times mod n is that it repeats after some period, and quantum interference is particularly good at obtaining this period. Now, one sample does not give us the period outright, but it lands near a simple fraction of it, and a bit of classical number theory turns a few such samples into the actual period and then the factors. Now, this is why factoring is vulnerable in principle. It is not magic and it is not doing everything at once. It is using interference to convert structure into information which we can pull out with a single measurement. Now, this idea appears to threaten RSA encryption since RSA assumes big composite numbers are hard to factor. But there is a big gap between the clean math of Shor's algorithm and the world we live in. Small toy demos often bake in shortcuts through use of classical pre- and post-processing or reduce depth in ways that do not scale. Real factoring at useful sizes need long, precise circuits and error correction, which means lots of reliable logical qubits built from many imperfect physical ones. Today's devices are far from that. And while quantum can expose hidden structure like periods, which is why factoring is special, the path from the neat period finding idea to breaking real keys runs through a heavy classical setup, a small but crucial quantum core, and hardware we do not yet have at scale. So we just used interference to pull out a hidden rhythm for factoring, and now we point the same idea at linear systems. Think of a real problem like a steady heat source diffusing on a grid, and it turns into Ax equals B, where A is big but sparse, and we care about features of the solution rather than every entry. A quantum linear solver encodes B as a state, uses control dynamics to weigh components by the inverse of the matrix's eigenvalues, reverses the setup, and leaves a state proportional to x. Now, a point to note is that we do not get the whole vector for free. We have to ask targeted questions like an overlap with some probe and repeat enough times to estimate it. When the matrix is sparse, well conditioned, and we can access it efficiently, the cost grows only polylogarithmically with the system size and polynomially with the condition number and target precision, which is why this line of work is exciting for optimization and some machine learning pipelines. A point to note though is that the preparation of B, encoding of A, and preconditioning can sometimes dominate, and success requires keeping only runs where a flag qubit clicks, and today's noise limits depth. Another angle we look at now is machine learning and its quantum variation. For the sake of this video, let's look at convolutional neural networks or CNNs. A classical CNN builds features with local learnable filters or kernels and pooling which help in feature reduction. After high-level feature extraction through a series of filters and pooling layers, the features are flattened and fed into fully connected layers that perform final classification of the input visual data. Now, a quantum convolutional neural network mirrors that structure with short local blocks that entangle nearby qubits and mid-circuit measurements that prune width. The surviving wires carry more abstract features to a small readout. This suits near-term hardware because blocks are shallow and local. You can treat the quantum part as a compact feature extractor that a classical head finishes. It can help on small problems with strong locality. Training still runs in a classical loop, and gradients can be noisy, so you can expect modest models rather than big end-to-end ones. Now, turning classical data into something quantum computers can work with is the hard part. Even a tiny 8x8 image means mapping 64 numbers into a single state on 6 qubits with many precise rotations and controls. The cost grows with pixels and with the precision you need. If loading dominates, any advantage from the quantum layers evaporates. So to resolve that issue, we use encodings that the circuit can prepare cheaply, compress early on with classical feature maps, and then aim for tasks where you only query a few overlaps or similarities rather than the full vector. If you need to push large images through many epochs today, a quantum CNN is the wrong tool. Again, on today's noisy devices, another difficulty is often the training process. With a global cost, the gradient can vanish and the landscape turns flat, so learning stalls. A practical fix is local objectives on small subsystems, which keep a usable signal so updates can progress. But depth needs error correction. Surface codes bundle many physical qubits into one logical qubit, with overhead growing roughly as code distance squared. That real cost sets what counts as useful. So with that, we come to the end of our video. We saw how quantum helps when the problem has structure that interference can expose, and when data access and errors do not drown the gain. The open questions are where the balance lands in practice. Will near-term chemistry or material simulation reach regimes that outspace strong classical methods? The field is moving fast, but we need clear benchmarks, less hype, and results that survive careful accounting. One thing is certain, you will not use a quantum computer to run your favorite video games or load high-resolution textures faster. That is not what these machines are for. If you want more straight talk and hands-on explanations, subscribe to Eigen Academy and stick around. We will keep exploring what works and what does not. And if you enjoyed this video, do give it a like and share so I can keep more videos like this coming. Stay sharp and I'll see you in the next video. Bye.